Let's write down the given. We have dimerization reaction, and then we have a second order reaction. K1, our first reaction, has 0.250 liter per mole per second, and we have temperature 25 Celsius, and we have the initial concentration of A 1.00 times 10 to the negative second molar, and then we have initial concentration of B 2.50 times 10 to the negative 2 molar. It was found that after each reaction has progressed for 3 minutes, so our T final is gonna be 3.00 minute, and at that time we observe concentration of A happens to be same as 3 times the concentration of B. A calculate the concentration of A2 after 3 minutes, meaning we have to find the concentration of this guy. Okay, so since we know this is a second order reaction, let me define that first. For second order, you have 1 over final concentration of A KT plus 1 over concentration of initial. When you graph this, you have T as an independent variable and 1 over concentration to be the dependent, and you should expect the linear graph rising above like that, and that K is the slope here. But to solve this, we have to just plug it in, and so step 1 is find the K, find the final concentration of A. Good news is that we have all the given except this A, F. We have K, that's good. We have K1, I should write K1. Okay, we have K1. We have time, 3 minutes, and we have initial concentration of A, and we can find a final concentration of A. Okay, here's something you have to be careful. Time here is not gonna be minute, because our rate constant, it has a second in the denominator, so make sure you convert 3 minutes to 180 seconds so that the unit can cancel out, like the S and the second and second, plus 1 over the concentration of the original 1 over the original concentration of A, which is 0.0100, but if you reciprocate that, you obviously know that that becomes 100, and then when you punch these numbers in calculator, you get 45. So you get 1 over, the F is the T equals 3, 180 seconds. You get 1 over, no, you get 145. And then all you have to do is reciprocate this, which is 1 over 145. Our final concentration of A is 0.00690 mole per liter. Alright, that's what you see after this reaction experience 3 minutes. Now they are asking the A2 here, so be careful, we are not done yet. Okay, So this is what you see, what you observe after t past 3 minutes. So we have to find how much concentration of A the reactant was used up to make our product A2. So to find the concentration A reacted, you have to subtract the initial concentration minus the final. Okay, so you have 0.0100 molar to start out, and then you subtract this much, and then we can find how much got reacted or used up in the first reaction, and you get 0.0031. The reason why I keep 2 sig is because when you subtract the our 3 sig and 3 sig there, this has up to 10,000 sig unit, and it has 100,000. So 10,000 is the smaller, so you have to cut off here. So you get mole. Okay. Once you know this, once you know that much of molar of concentration A was used up, all you have to use is use a stoichiometric relation. So looking at our first equation, I see every 2 mole of A react, you get 1 mole of A2. So I put 2 mole of A because I see 2 in front, and then 1 mole of A2. You cancel out the unit. Oh look, we have answer. When you divide that, you're supposed to get 1.6 times 10 to the negative third. Yeah, and that's molar. So that's our answer to part A. Now moving to part B, we have to find the value of K2. K2 is the second equation as you see above. Okay, it's the second equation. So for part A we dealt with the first, part B we're dealing with the second. Okay, so let's write down the second order reaction for our second part, second equation. So I'm gonna define it as 1 over B at t equals 3 equals K2T, which is at 3 again. Well, I'm gonna plug that in later. Plus 1 over initial concentration of B. Okay, what are given? So we have the initial concentration of B looking up. Okay. So we have this, and we don't have K2. Actually, we are looking for K2. We know T final. Oh, here's another useful. Okay, this is implied at 3 minutes. So from part A, we found the concentration of A, and we can find the final concentration of B by multiplying 3, or actually dividing by 3 of our concentration of A. Then we can find K2. How nice. Okay, so let me reiterate. We have this, we have that, and we have that. Alright, so I'm gonna plug it in. 1 over, okay, remember it was 3 times. Okay, so you have to divide it to find the concentration of B. So let me write here. So you get that. this is a 3-minute concentration, and we got that as a 0.00690 from part A here. When you plug it in, you should get 0.0023. Okay, keep 3 sig. So that thing will go here. 1 over 0.00230 equals, we don't know K2, which is what we are looking for. Again, keep second and plus 1 over initial, turn out to be here, that's our initial, 2.50 times 10 to the negative 2. Okay, when you rearrange it and then find K2, you should really get, okay, K2 should be 2.19 liter mole per second. So that's the answer to our part B. And part C, calculate the half-life for the experiment involving A. This is a lot simpler than other parts so far because we just have to use the formula, and second half-life for any second order rate reaction has to be 1 over K, 1 over times the concentration of A initial. Because we are doing A, we don't need to be concerned with the second equation. That's why I put the 1, not 2, K1, not K2, and I use A. Oh, we know K1, actually they both were given. K1 was, looking up, K1 was 0.250. And then our concentration, initial concentration was 1.00 times 10 to the negative 2. When you do this, you get 400 seconds. You should keep 3 sig, so in scientific notation you could do 4.00 times 10 to the seconds. So that's your half-life.